So far we have seen how to use Venn diagrams to calculate probabilities, and we have seen how to use tree diagrams to represent the possible outcomes, but we have not seen how to use tree diagrams to calculate probabilities, and that's the objective of this lesson. Assume that we have this area of 100 households where 35 of them don't own pets, but 40 own a dog only. 5 have owned both pets and 20 own a cat only. In this case, we know that the number of people that have a cat is 25. Cats only, and those that have a cat and a dog. So the people that would answer yes to the question, do you have a cat, is 25. And similarly, the number of people that have a dog is 45, and the number of people that have both a cat and a dog is 5, and so on. So we want to consider asking somebody at random from this house, this area, and we want to ask them, do you have a cat? What's the probability of them saying yes? Now, we know that the number of households is 100, so the probability of owning a cat would be this 25 divided by 100, giving us 0.25. The probability of owning a dog would similarly be 0.45. The probability of owning both pets, a cat and a dog, is 0.05, and this is pretty obvious, simply obtained by dividing these numbers by 100. So let's answer the following questions. What's the probability that somebody asked at random from this neighborhood would have no cat and a dog? No cat, we're dealing with these people here and here. So no cat and a dog means we're talking only about these. So 40 divided by 100 is 0.4. Simply locate the region and divide the number of people in that region by 100. What's the probability of picking somebody that has a cat and no dog? Obviously it's 20 alone, because those people don't have dogs, so and they have a cat, so it's 0.2, and the probability of no cats and no dogs is 0.35. So let's add the probabilities, the 0.4, the 0.2, the 0.35, and the 0.05, and they all add up to 1. And that's only to be expected because they cover the possibility space. Now let's try and construct a tree diagram. And let's imagine that somebody is standing at the corner in this area and begins by asking people a simple question. Do you have a cat? The possible answers are, yes, I do have a cat, or no, I don't. So the outcomes are C, C prime. Now what's the probability of owning a cat? We have just calculated that it is 0.25. What's the probability of not owning a cat? Well, you can use the rule, the probability of an event plus the probability of its complement add up to 1, giving you 0.75, or you can work out the probabilities from here. Those have a cat, those have a cat, those don't, and those don't. 40 plus 35 is 75, divide by 100, and that gives you the 0.75. Now remember, those are the probabilities that you have before this person answers the question. Now let's say you ask the question and somebody says, yes, I do have a cat. then immediately you would know that this person is one of the people in this set, the set of cat owners. So this answer reduces our possibility space. And then let's ask a follow-up question. For this person who said, yes, I have a cat, okay, do you have a dog? And the possibilities are, yes, I have a dog, or no, I don't. So what's the probability that we put on this branch? Because the possibility space has been reduced, this is a conditional probability. For this set inside the red, what's the probability of somebody owning a dog? It's obviously a 5, because this is the favorable outcome, divided by all the possible outcomes, which is 25. So the probability that we have here is 5 over 25. And I'm not simplifying the numbers, just to keep us aware of where they came from. Similarly, this person might answer by saying, no, I don't have a dog. In this case, the probability is 20 divided by 25. Again, note that the sum of the two probabilities on the two branches is 1, because the person might have a dog or might not. Those two are complementary events. Now, assuming that this person said, no, I don't have a cat, and we follow up with the question, do you have a dog? And the possible outcomes are, yes, I do, or no, I don't. In this case, if this person says, I don't have a cat, then we are talking about with somebody from this group or from this group, whose total is 75. What's the probability that one of them will have a dog? The favorable outcome is 40, the total is 75, so the probability is 40 over 75. And by thinking of the complement, this is 35 divided by 75. Now, let's multiply the probabilities. And let's take the first branch, this branch. What's 0.25 times 5 over 25? It's 0.05. Let's take the second possible root, this root. The product of the two probabilities that we have here is 0.2. Similarly, if we think of this root, the probability is 0.4, and if we think of this root, the probability is 0.35. Add them up and you get 1. This is the entire set of possible outcomes. But we have seen these numbers before, right here. And we can recognize the numbers. This is the probability of a cat and a dog. This is the probability of a cat and no dog. This is the probability of no cat and a dog. And finally, this is the probability of no cat and no dog. Let's consider the first branch only. What is this probability, the 0.25? Obviously, it's the probability of having a cat. And what's this probability? It's the probability of having a dog given that you have a cat. So it seems pretty obvious that when we multiply P of C times P of D given C, that equals probability of C intersection D. Let's see if this works here. The probability here is the probability of D prime given C, and the product of P of C times P of D prime given C equals the probability of C intersection D, and the same rule holds. So generalizing for what we call consecutive events, where the outcome of the first event is either A or A prime, and the outcome of the second event is either B or B prime, we can express the general rule as the probability of A intersection B is equal to the probability of A times the probability of B given A, which is basically the product of the probabilities that are on those two branches, where we put on this part of the branch P of A, and on this branch P of B given A. And this is the general rule that we use. So how do we use this? Now let's say that the probability of it raining is 0.1. And if it's raining, so that we have the probability of rain and the probability of no rain. If it's raining, there's a probability that I am late, and that probability is 0.3. If it's not raining, I might be late, I might not be. If it's not raining, the probability of me being late is 0.2. So as you can see, rain delays me a little bit. If that's the only information I have, then I can complete the probabilities on the Venn diagram. I know that the sum of the probabilities on those two branches must be 1, so this is 0.9. Here, this is 0.7, and here this is 0.8. So I can ask the question, what is the probability that tomorrow it will be raining and I will be late? And this is simply achieved by R intersection L, which is this root, raining and I will be late, and the product is 0.1 times 0.3, which is 0.03. Find the probability that tomorrow it will not be raining and I will not be late. In this case, the probability of no rain and not being late is simply 0.9 times 0.8, which is 0.72. And that's how we use tree diagrams.